How we doing this morning? You look all so high energy. Every last one of you. Do some demos here today. Is all active. All right, making sure everything's good and streaming. Let's start the recording. Hey, DJ, can we start the recording as well? Quick. Thank you so much. All right. Glad to have you this morning. You had an all right weekend? Yeah, just we're so low energy. We can't have this. What's that? Wonderful turnout, as we can tell. All right. It's all right. Your attendance is appreciated on the sheet as well. So thank you. All right. So, all right. So a couple things. So as you all know, you'll have your homework that's due tomorrow. It's a shorter homework. I see people have largely been making good progress on it when I've talked with them. Okay. Let's cover a little bit. There's a couple questions I think people had that I think are worth addressing with everyone. So I'll hit those at the beginning of lecture. Next we will have our normal coding stream on Thursday. It'll be Zoom, okay? And next week is spring break, right? I mean, who's counting, right? So there's no obligation to be on campus for my classes on Thursday. I'm just pointing that out, okay? It's a small fact, all right? So we will be doing things over Zoom, as usual, for the coding lectures. So just a little bit of background today. Let's go here. All right. 2026, 03, 10. So for your homework, you're doing a lot of linear programming, right? You're doing things like, hey, so for your linear programming homework, okay, you're doing a lot of things like, hey, let's look at a plot where you have some decision variable W1, some decision variable W2, or X1 or X2 or whatever, right? Okay? And I'm saying things like, oh, create a constraint which looks like those lines or something. Or maybe it's the inside of a pentagon, right? So, or let's say it's the inside of a square. How would you make linear constraints that say, hey, I want a rectangle. I want my variables inside of that rectangle. Well, you could create a constraint line like these two, and then these, and say it must be, you can't be above that line, can't be below that line, can't be below that line, can't be above that line, right? Oh, well, look at that. What's the only place that's left available? That little quadrilateral, all right? And so when you're defining those constraints, you look at this line and you say, oh, that's a line right there. Hey, I know lines. I'm a senior level mechanical engineer. I know what a line is. It's y equals mx plus b, right? And you can write that y equals mx plus b for all of those, for all those lines, right? Those are linear constraints, and you can turn them into linear constraints for your linear programming problem, which is going to look like this. Some w star is some argmin of some c transpose w, subject to some constraints. A, w is less than or equal to b, right? That's your linear programming, your linear programmer, LP, right? It's got the linear cost as a linear constraint, okay? So you take all of if you have your linear constraints, you write them in this form, and you turn them into this form like we did in class. Get an A and a B matrix. You can compute the Jacobian if you want to get the A matrix and the leftover terms of the B matrix, or you can just rearrange them appropriately, okay? But that's just setting up the problem. So if you have C, A, and B, you can then use linprog in MATLAB to solve. And you give linprog C, A, and B, where C is a vector, B is a vector, A is a matrix, right? Okay. And it does all the solving. That's great. Okay. But part of the homework is also, I'm asking you, what cost functions will drive the solution to different places. Let's say that these are all your constraints here, right? But you want that, but I said, hey, what cost function will get you that solution? Okay? And you have to remember, what is a cost function? It's the thing you want minimized when you're solving the problem. So if you come up with a cost function such that when it's minimized, it goes to the lowest possible point right here, voila, you have a cost function that drives you to that point. So what would be an example of such a cost function? Any guesses? Yes. Close. You say, in this case, W1. Let's say you want to minimize W1, okay? That means it's going to try to push you to the minimum possible value of W1 that's allowed, right? Right? And where is that? Back in this direction, right? Oh, no, it's okay. It's more, okay, I know what you meant. You meant W2, right? I'm sorry. I apologize. I misinterpreted your words literally. I should have taken them. You made your numbers wrong? No, look, I'm the one on camera. Let me take the blame. Okay? All right, you're good. W2, though, you're absolutely right. W2, you want to minimize W2, you go in that direction. You go down there, right? Gives you a visual understanding of what's happening with linear constraints, right? And the beautiful thing about linear constraints is that, like, in your head, you could be like, hey, let's just find the lowest possible point. And that's going to be one that this convex optimization finds, because there's no nooks and crannies that you can get caught in. There's no little magic finger that looks like that's constraint. You're not allowed on, you can't go there. If that were the case, you could get caught at this little local minimum there, right? Right? But because they are linear constraints, no matter how many linear constraints I draw, doesn't matter. I'm going to find the lowest possible point in a linear program. Okay? And that's the beauty of linear constraints. And I feel like this is worth reiterating. So yeah, the beauty of linear constraints is that the admissible set, that's where you're allowed to be, okay? The admissible set that's where you're allowed, you know, everything that isn't crossed out here, right? That's the admissible set. If defined by linear constraints, is always convex. And thus has no nooks and crannies, you know, to get caught in local minima. Okay? I think this is worth reiterating. It's one of the beauties of, it's one of the things that made it click for me, how this can be so efficient. How you can have an optimizer that just looks for local minima, and yet it finds the global when you have linear constraints. Let me just draw just a two-dimensional grid of two decision variables, W1 and W2. Okay? I'm going to draw just some linear constraints. They're inequality constraints. They can be equality constraints too. Nothing's stopping you there. Okay? All right? Let's say we're just trying to minimize W1. It would drive you to the lowest possible point. W2. I did it. See? I said W1. I meant W2. See? It was me all along. I'm the villain. Okay? All right? Want to minimize W2, you go there. Want to minimize W1, it'll keep going off in this direction. All right? Okay. Now if I add another constraint, the set is still convex. There's no nooks and crannies. Recall that a convex set means that I can just draw a line from any point to any other point, and every point in the middle is within the set. Beautiful, right? I don't care how many lines you draw. I challenge you to draw a line that makes this set not convex. It's impossible. Beautiful. Okay. Now, why am I harping on that today, other than the fact that it's in your homework? Okay, is because this has real implications for control and direct collocation, which we covered in the last set of lectures. Okay. Now, you will recall, hopefully from your notes and your indelible memories of me yelling at you about it, okay, that direct collocation is interesting and special because it doesn't use simulation to determine where your system is going in the future. It uses constraints, what we call defect constraints. All right? And those defect constraints tell you, basically their job is to say that if I have a trajectory, so let's go back to trajectory optimization. Back to trajectory optimization, where we have some u of t over time, which is our input, control input, and our state over time. And we're trying to optimize some trajectory, right? Okay. In direct collocation, we don't get this via simulation. We don't know what the state moves over time via simulation. With direct collocation, we create what we called collocation points along the way. Collocation points. And we looked at the tangent line at those collocation points. And the slope of that line, the direction that it's moving, the slope is the change in x over time, x dot. That's our physics. Direct collocation was so weird because it doesn't use simulation. It instead checks at points along the trajectory and says, hey, is it moving with physics? And we enforce that with a constraint. Wild wacky. Okay, we'll code it up on Thursday together. All right, from scratch. Isn't that fun? You code up everything from scratch in this class. All right? We just finished coding up multiple shooting from scratch in this class. And you learned how to debug on the fly, which I totally intended in class. It's actually part of the experience, right? So we'll code this up on Thursday. But the point is that physics, so in direct collocation, physics is enforced via constraints, not simulation. So I ask you, my friends, wouldn't it be nice if these constraints that we're talking about are linear? Wouldn't that be nice? Can anyone think of why that would be nice? Wouldn't it be nice if we could wake up and all of our constraints were linear? Okay. All right. Anybody got any ideas? Yeah. It could be blazingly fast. Yes. It could be a really fast optimization because you could use a local solver and it will get you right down to the minimum, right? Of course, it also depends upon the cost function. But who gets to choose the cost function? We do, right? We could choose a linear cost function. We could choose a quadratic cost function if we thought it was good, right? And then all of a sudden, it's a quadratic program or a linear program. Excuse me. And it should solve very quickly. That's nice, right? So I ask you, what if we could make those defect constraints linear? It'd be a very fast and reliable optimization. Okay? And to demonstrate how awesome this is, I'm going to need a volunteer that's comfortable with being on camera, okay, for a demonstration. Anybody? All right. Okay, you were first, okay? All right, come on up. All right, give our volunteer a round of applause. All right, let's move over here. All right. Okay. Good morning. Good to see you. All right. So, okay, we are going to explore the implications of being able to do a trajectory optimization really, really fast, okay? All right, you, my friend, are a smart person, capable, we all know this, I didn't have to say it out loud, right? Okay, you are going to do a trajectory optimization in your head. Basically, it's fine. You do this every day, right? For instance, I'm gonna give you a task. Okay, your constraint, my friend, is I want you within a few seconds, if you get to stand right there, okay, and come to a stop. Your cost function is whatever you want. Okay, can you do that for me? Okay, I would like to, have you optimized it in your head? I have. All right, could you execute on that optimization, please, right? All right, fantastic. All right, well, round of applause for our optimizer, fantastic. All right, you can go back to start, please. Back to start, we're resetting. All right, thank you, reset. All right, so you had a plan. That was a plan, right? You optimized it, that was your plan. You can call that, but you did not change that plan at any point, really, did you? No. Good, okay, I asked you not to, so off camera I asked you not to. All right, so we would call that feed forward control, right? Because he just has a plan, something he's gonna do for some period of time, okay? I did not ask him to change it up based upon things that are happening, okay? All right, now, come up with a plan to do the same thing, all right? You got the plan in your head? Yeah. Okay, now take one step of that plan. Okay, all right, stop, okay? Now, what's your pause? Do you want to re-execute? You want to continue? Once is a strong word. It's a smart idea for you to continue. It is not. You don't want to run into the professor who controls your grade. No, right. You don't want that, right? Okay. So wouldn't it be nice if you could replan? So why don't you take a replan, come with a new plan to get to that same spot? You got the plan in your head? Yeah. Okay, you took one step. Now, okay, now take one step of it. Very good. Excellent. Okay. All right. Now, come up with a new plan. All right, you got a plan in your head? I do. Because you're smart, you figured it out quickly, right? Take one step of it. All right, keep going. Now finish off. Fantastic. All right, thank you so much. All right, that's the demonstration. So what he was doing was he was measuring the state of the system and replanning all the time. And because he's smart and quick in his brain, he was able to replan super fast. We ran some trajectory optimizations in our lectures on Thursday, and sometimes they could take, you know, a minute, right? They could take a minute. He didn't have a minute. But because he's so fast at replanning, he could replan constantly when things changed, when his state changed. So he made the trajectory optimization not just a feed-forward controller, an open-loop controller where there's no feedback. He turned it into a feedback controller. He measured the system state and would constantly replan. And that's what you can do with trajectory optimization if you make the constraints linear. The optimization is so fast you can do it in a loop over and over again. That is the essence of what we call model-predictive control, MPC. It is the coolest controller with the slightly uncoolest name around. That's what he did with something we call MPC. Okay? And the idea is that instead of an open loop trajectory, which is what a trajectory optimization will give you, it'll give you, if you give it a set of constraints, a cost function, and constraints, it'll give you some input trajectory u of t. Okay? Trajectory optimization, traj-opt, becomes part of a feedback loop. Okay? So it'll be closed loop. So the idea is that you have some state x of t. It goes into some trajectory optimization TO. You got to give it some cost J of W. I want this all go all the way in, excuse me. All right. And some constraints G of W. And out of a trajectory optimization pops your control. Then it goes into your physical system, which you'll recall from our early lectures was called our plant. That's the physical system. It's a fancy word for it. Just recall that from the early lectures. And then it out comes as some whatever state you have. But then you measure it and loop it right back around. Okay? That's your feedback loop. So there's some rate of this feedback loop that you measure your state, then you update your trajectory optimization with whatever your new state is, you rerun it, get a new set of control inputs, your plan of what to do, and then it goes into your plant. And you see what happens, and you just do it in a loop. So you could think of model predictive control as just trajectory optimization in the loop. Okay? Why is it called model predictive control? Okay? It's because you have a simulation model in your head. You have the physics of what you're made of in your head. Our volunteer knew that he could take steps, he could move in a certain way, right? And was able to predict into the future where he was going to go, right? That's the model prediction. And the control uses the model prediction. That's where the name comes from, okay? So now I showed you this in terms of a demonstration there. Let me see if I can just move back to here for a moment. Try to see if I can pull up an example here. I know I've showed you all this in the past. All right. Okay, back to see that. Okay. So here's a drone in our laboratory using model predictive control. It's literally doing the example we had here. Instead of the professor being in front of you, it's a little pendulum we had swinging at the drone. We're telling it to stay in the center position. We give it constraints that it can't touch the obstacle. And so the way it does it, we have our own sort of fancy little way of making all the constraints linear in our optimization problem. That's why you're going to see a lot of lines here. Okay? Look, that's that little dashed line. That was the plan. It's always updating. Okay? Look, and because the constraints are linear, you can add tons of linear constraints and it's still convex, which means it still runs pretty darn fast, right? So we have a bunch of things chasing it, right? Moving around. And it executes really quickly, right? Okay. That's like the mathematical version of it. Okay? And we'll show you, and it works for any system that you will find where you can make the dynamics linear. That's how you make the constraints linear. The dynamics have to be linear. And so here we can show it actual hardware, and these two drones are basically playing tag, more or less. And you can, and that blue drone's trying to stay in the middle, and this red drone's chasing it down, which is the PD control law. But here, you can see the blue drone's thinking. That's the model prediction. That blue line, that's the path. And that's being computed with a quadratic program, okay? It's rerunning it, many times a second, and it just measures, hey, where am I at? Where's the other drone at? Where are the states? And it extends the 3D just fine. It's just more dimensions in our linearly constrained dynamical problem, right? Whoop, it just zips over it, right? Okay. So Okay? Isn't that pretty neat? So we'll code that after we get back from spring break because it requires that we code up direct collocation first. Okay? So to run the MPC loop fast enough, we need a linearly constrained program. Linearly constrained trajectory optimization. Okay? Okay? How do we do that? We have a few conditions, okay, to make a linearly constrained trajectory optimization. Conditions. The system dynamics are linear. Okay? And two, the time horizon, that's how far into the future that our trajectory is looking, is of constant duration. Is constant. Okay? I say that because in our examples of trajectory optimization for our little drag race problem, where we are taking our, oh, you can't see that. That's right, people on the board can't see that. I apologize. All right. So, okay. All right. So we have to run the MPC fast enough. We need a linear constrained trajectory optimization. Conditions, system dynamics are linear. Time horizon for the trajectory is constant. Okay? Why is that? Because in our examples, in our coding lectures, our time horizon wasn't constant. Remember we had the drag race problem? We're trying to get from A to B. What were we trying to minimize in that problem? Anyone remember? Time is a race. Minimize time, right? So the time duration was a variable in our decision vector. It's something we could change, right? In MPC, to get your linear constraints, you have to give it a constant. It's very typical, at least very typical, to give it a constant time horizon. And you can see that in the video. If you look into the length of that line that the drones were thinking through, that was a constant time into the future I was looking at. So when the line was like non-existent, it just predicted it was going to stay in place, you know. So, all right. So, and why is that? So let's go back to direct collocation. Direct collocation. Okay. So where you enforce physics as constraints. Okay. And let's, for example, we're going to use just explicit Euler, or forward Euler integration, just because it's super easy. We have all our other fancy versions. We have all the implicit Eulers, the trapezoidals, Hermite-Simpsons, all the things we talked about last time. Let's use an explicit Euler example, where the next state, xk plus 1, is equal to xk plus x dot at k times some delta t. Okay, it's often called h, but here I'll call it delta t just for obviousness' sake. Okay, all right, that's the time step, right? Great granddaddy Euler says, hey, where am I now? How fast am I changing? How long am I changing for? That's where I'm at. Okay? Now, we do recall that x dot of k is going to be some function of x of k and u of k. That's your dynamics. Okay? If it's linear, or LTI, what's LTI stand for? Can anyone remind me what LTI stands for? Linear time invariant. That's right. Okay? X dot is equal to a xk plus b uk, right? Therefore, xk plus 1, let's substitute these dynamics here right into our dynamics there. Whoop, whoop, shoo. That's where we want to put them. Not too bad, right? xk plus axk plus b uk times delta t. Okay? All right? And for a direct collocation problem, okay, keeping in mind our decision variables are not just going to be our control inputs, it's also what, friends? What do we include in the decision vector for direct collocation that we wouldn't for, say, single shooting? Anybody? You only have to include control inputs, that's it? States. Got to include states, right? So that means xk, that's a decision variable. uk, that's a decision variable. And everything I'm looking at here, this is just a linear combination of decision variables. Unless, my friends, there's a decision variable in there. If you multiply, so is there a decision variable in there? Well, if you have n points on your trajectory, right? That would make delta t equal to the total time of your trajectory, capital T, your total period, your time horizon, over n minus 1. Okay? Therefore, xk plus axk plus b uk times quantity t over n minus 1. If t is a decision variable, this is no longer a linear constraint. Because you'll have t, a decision variable, multiplied by uk, which is the decision variable, right? So this cannot be a decision variable. A decision variable. Okay? That means if that's a constant, then no matter what time we're at in running our controller, we're always looking the same amount of time into the future. Okay? No matter how much time passes, right? We're dancing around, you know, the drone's moving around, going from place to place, okay, trying to go. It's still thinking, I don't know, 5 seconds into the future, whatever time horizon you set, okay? All right? That time horizon is always moving away from you, right? Even though you think you're getting close, it keeps moving away. It recedes from you, okay? So the term people use is they call it a receding horizon. There are people who call this kind of control receding horizon control. That means that the time in front of you is always moving along with you, right? There's no time where that comes and collapses to you and say, I'm done, right? A controller's job apparently is never done. You keep running it. All right? So that's your constraint for MPC. If you have linear dynamics, LTI makes it easy. Theoretically, you can get away with linear time varying. That's something you can do. We haven't covered that yet. But that's your LTI dynamics. Okay? And guess what? Linear constraints for your trajectory optimization problem. Okay? All right? But to be convex, the cost function should also make the optimization convex. All right? So if it's linear, it's a linear program. If quadratic, it's a quadratic program. Now, keep in mind that it also has to have a positive Hessian, meaning it has to be concave up. Okay? We got that by checking the eigenvalues. Most of the quadratic cost functions that you deal with in control tend to be concave up. Classic examples, all right, of quadratic optimizations, quadratic costs. Squaring your control input. That's an efficiency term. Okay? Also, let's say you have some x desired minus x of t. That's an error term. Where you want to go versus where you are. Minimize error. Guess what? Those are all going to be concave up. And that's good news. It's a convex quadratic program, so it'll run fast. That's what we do precisely with that example I showed you with the drone. Okay? I threw a lot at you for the moment. But we'll code this out in class after we do cover direct collocation. Any questions so far? Yes, Marco. Yeah. So the question is, what if your system's nonlinear, right? Yeah, you can linearize it, right? But if your system's very nonlinear, how the range for which that linearity applies might be terrible, okay? So it's something you got to take into account. So there's limits to what you can do with model predictive control, because if you have a nonlinear system, your trajectory optimization is very nonlinear, right? Okay? But there's a cool approach that people use that makes it even better. So I'm going to pull up. So imagine we have, so let's look at our drone, okay? Example of our drone, right? Look at my beautiful drone, little quad rotor, okay? We modeled it as having linear dynamics effectively. Actually, DJ in the back of your class actually pulled off those experiments, by the way. He's such a, that's how awesome he is. He pulled those off. Were you an undergrad when you were coding that up? Yeah, he was an undergrad when he coded that up. All right. So we modeled this as having linear dynamics, but let's imagine that we didn't, okay? Let's say we linearized our system, okay? And you can linearize, you have to linearize your system about what? An operating point. You have to choose a state and a control input you want to linearize it about, right? Let's just say we choose one, okay? We choose one. Maybe it's not very valid for very far away from the operating point. Let's say it generates a trajectory, okay? Here's just some x and y trajectory, right? And your prediction has all of these points along the trajectory, those little points. That's the trajectory where it thinks it's going to go, right? It runs that trajectory optimization and said, great, I'm going to then execute on the first step of that trajectory, and then rerun a trajectory optimization with my dynamics, right? But here's the thing. I now have a prediction of what my future states might be. So I can update my linearization with these new operating points, okay? So you can iteratively update your linearization based on your prediction, and that's what a lot of people do. Anyone's seen, I think up until the last 18 months, you know, those Boston Dynamics robots, the humanoid robots that jump around and do parkour. I know I've shown them a couple times, right? They use model predictive control. Very nonlinear dynamics. What they are doing is they're constantly relinearizing. They say, okay, I have a linearization. It's going to be good for just this right here and now. It's only going to be good for this very narrow region. I'm going to make a prediction into the future. All right, then I'm going to be in this pose in the future. I'm going to relinearize about that pose. And it's doing that over and over and over and over again. It's incredible, okay? And those optimizations, even though they are quadratic programs, they're still huge quadratic programs. So they actually took existing quadratic programming solvers and like tore it apart and like try to make it as efficient as possible in the code to run as fast as possible on that robot. Okay, that's how it's able to dance. Okay, kind of wish I had a video up for this to show that, right? So if you look at like the robot dancing, so if you want to, so if you look at, so it's called Atlas. You know, dances. And it's like, "Do You Love Me" is the song. Okay, right? It's using model predictive control to do all that. Okay? So you can relinearize along the trajectory. With new operating points. So just because it's a nonlinear system, there are still smart ways to use model predictive control. Okay? Well, let's break it down into steps. Okay? All right? So MPC in steps. Okay? Step 1. Measure your current state. Number 2, formulate a trajectory optimization problem with finite horizon and your current state as an initial condition. Number 3, solve the trajectory optimization and obtain an optimal U of t, control input, right? Then you just want to take a little step of that control input. Okay? So execute U of t for a small sampling time TS. And then step 5 is you repeat. You go to 1. This is exactly what our volunteer did, right? Says, hey, where am I? What's my situation? Set up a trajectory optimization. Solve that trajectory. Come up with a plan. You execute some little amount of that plan. One thing that's typical is you just do it, is you only execute from between your little trajectory optimization points, from one point to the next. That's a good heuristic. It's a good baseline to try to start with. But it could be anything less than the total trajectory, right? Then you go back to step 1. Rinse and repeat. Keep doing it. Okay? All right. Any questions so far? Well, let's actually write out one of these optimization problems. Okay? So let's write the decision vector cost function and constraints for a model predictive controller. Okay? And let's do a really simple style of problem. Let's just say we want to move a block. This will be our drag racer again. Okay? Where we apply some control input u of t to a block. And we wanted to get to some s final. This is s of t. Right? Okay. We're going to use explicit Euler and direct collocation. Okay. So our constraints are going to be our next state xk plus 1 equal to xk plus x dot of k times delta t, sometimes known as h, more commonly known as h. I think delta t is a little bit more intuitive. Change in time, delta t, right? H is your time step. Okay. Now, this is our state, of course, so we need to know what our states are. We've done this a billion times. I should come up with a different example. We're going to say that x of t is going to have our two states, s of t, s dot of t. And the derivative of that state, derivative of s of t, is going to be s dot of t. That is the state. That's great. Okay? And if we have a mass, our acceleration, s double dot of t, is going to be 1 over m times our force u of t. That's just our physics, right? Okay? In our time step, if we have n points on our trajectory, delta t is going to be equal to n. Sorry, is going to be equal to our final time, t, over n minus 1. Just recalling that if we have time, here's our state. We have 1, 2, 3, 4, 5, 6, 7, 8, n. That means the number of points connecting them, the number of shots connecting them, or connecting points is n minus 1. Where it comes from. All right. Therefore, okay. All right, so we have that delta t is equal to t times n minus 1. Let's write this. Since these are linear dynamics, they're LTI. Let's write them as x dot of t is equal to a x of t plus b u of t. All right, so we got to figure out what our A matrix is. Excuse me. Now, anyone want to guess the size of our A matrix here? How many states we have? 2. Is the A matrix always square? It is always square. So it's going to be a 2 by 2. Okay. If we practice our Jacobian skills, the partial derivative of our recall this is all equal to the partial derivative of our dynamics, f of x u, with respect to x evaluated. So that, yeah, there we go. Okay. So the derivative of our first set of dynamics with respect to our first state, there ain't no s's in our s of t, is 0. Now we are on the second column. So first row, second column. So it'll be s dot partial s dot. That's 1. Onto our second row. Partial of this, partial s. I don't see no s's. And I also see no s dots. There we go. That's our A matrix. In our B matrix, It's going to be a 2 by 1. That's the partial f of xu, partial u, our control input. So our first row, partial u, I don't see any u's, so it's 0. Oh, look, I see a u, coefficient 1 over m. Okay? Therefore, I have a constraint where xk plus 1 is equal to xk plus quantity a xk plus b uk times delta t, which we know is t over n minus 1. Okay? This is our time horizon. Those are our constraints. I jump straight to our constraints. Those are our defect constraints. Defect constraints for all points k is equal to 1 through n minus 1. Every point k along the trajectory, except the last one. Why? Well, if you only have n points, that's going to ask for n plus 1. Doesn't exist. Okay? Those are your constraints. Are those constraints linear? Yeah, they're linear. Assuming that A and B don't have decision variables in there. If they do, you screwed up, or it's a nonlinear system. Okay? And assuming that you have a constant time horizon, that's not a decision variable. And if no one's asked to make n a decision variable, that would have been a disaster. N has to be an integer. Oh, save that for another year. Okay? Don't make that as part of the optimization problem. Okay? Those are our defect constraints. Okay? All right. Now, here's a little bit of trickiness about model predictive control. And you're like, but Christian, it's so easy so far. There's no wrinkles to this crazy model predictive controller. I could have done this in my sleep. I agree. You could have. Okay? How do we tell the block to go where we want it to go? Right now, we told it what its physics are. That's what the defect constraint does. It says, hey, these are your physics. Obey physics, please. I agree. Obey physics. We got to tell it to go somewhere. How did we tell the optimization to go somewhere in our prior trajectory optimizations in class that we coded up for this drag race problem here? Anyone remember? How did we tell it we wanted to go to the end? Was it in the cost? Was it in the constraint? What was it? Anyone remember? I know every second of this course is burned into your brains. Yeah. It was a constraint, right? We told it with a constraint, you got to end up there by the end of the trajectory. Here's what I'm going to tell you. With model predictive control, that's a bad idea. Why might that be a bad idea? The reason is that we had to decide beforehand how long into the future we're going to go. We're going to look. What if I told it too little of a time? What if I told it you're going to look 1 millisecond into the future? Do you think I'm going to be able to get there in a millisecond? No. I'm sorry, you just made it a constraint, though. The optimization is going to fail. It's going to fail. That's bad. Your controller, oh my goodness, this is long. This controller, this is in the loop here. Imagine your optimization keeps running. Like, I can't find a solution. And when it doesn't have a solution, what does it do? That's bad. So, because it is possible to give it an impossible problem, right? I could give it a constraint that says, hey, your control input, what's your name again? Yes, you. Taylor. Okay. You're my optimization. Okay. I'm telling you, my control input, the force, it's got to be greater than 1. Is that cool? But it also has to be less than -1. Are we still cool? Can you make a number greater than 1 and less than -1? No, you can't. We're not cool. I'm sorry. I thought we were cool, Taylor. Yeah, that's all right. You can, even though those are both linear constraints, right? I still made it impossible, right? That's an example. So it's very important that you give it an optimization problem that you're sure it can solve. But wait, but how do we get, so let's write that down real quick. So you have to be careful. So the note, you want to include constraints only if you are sure you can solve them. All right? So the Dr. Hubicki hack, or just general hack for that, is that you don't put constraints on states. Okay? So trick, don't put constraints on states. Okay? You can put constraints on inputs. Okay? That's totally fine. You tell it, I want to have a limit on the amount of force I want to apply. That's great. Just don't tell it that it has to go somewhere by the end of that trajectory, or it fails, right? But how do you get it to go where you want it to go? You put incentives on states in the cost, right? In the cost, you're just doing what you tell it, do the best you can, right? If I told it, hey, get as close to this box as possible, in the cost, it'll do its best. If it doesn't get all the way there, it doesn't break the optimization, it just got as close as it could. I see a mouth agape. Does that make sense? I would say it also includes workspace. Talk about going outside, and I'll tell you why. Okay, let's go out to, all right. I need a volunteer. You're up. Come on up here, okay? All right, big round of applause for a volunteer. It's early morning here. I have 15 minutes left. Great, we're flying through this model predictive control lecture. We'll stand you right here, okay? All right. Okay, this time I'm being controlled with model predictive control, not my student. Yeah, not my student, right? Okay. So so you're talking about constraint on workspace, right? Meaning don't leave a certain area. Is what you mean? Okay. Yeah. All right. Look at me. So my workspace is going to be everything but you. I don't want to hit you, right? Okay. So I could try to put a constraint on you to not hit you. That's basically what I did in that optimization problem there. But anyway, blah 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 blah. Deal with that. Okay. But so I'm using model predictive control. I want to go over there, trying to avoid you, trying to avoid you. Let's say I want to all of a sudden go over there, and I have a huge velocity in your direction, right? I don't have enough braking force to stop me from hitting you, right? And if I told in the constraint, I am not allowed to hit you. I'm not allowed to leave my workspace. The optimization will fail, okay? There's nothing I can do. What do? Nothing. optimization fails, it's going to hit you. Okay? So even something like leaving the workspace, let's say it's just leaving that space right there. I'm moving around and I find myself in a position where I'm moving fast enough. There's nothing I can do to decelerate to get out of there to stop myself from leaving the workspace, right? So now, will it try its best? Probably. Probably. It might, like, you could try putting the constraint on there. Don't hit you. Don't leave the workspace. And it'll do its best, but it might fail. And you want to make sure when it fails, it's not the optimization that fails, right? It's just like, well, I did my best. It's done. And when you want to do something your best, where do you put it? Cost. Okay. Make sense? Thank you very much. I appreciate you coming up there. All right, thank you. Thanks for our volunteer. Just have me yell at him in person, right in front of there. Thank you, thank you. All right, cool. So be very careful. A trick: just don't put constraints on the states. Probably not a good idea. Right? You can put constraints on inputs, and you can penalize states in the cost. That's what we're going to do now. We're going to penalize it in the cost. So we can put limits on the inputs. So we can say that u of k, uk for all k is greater than some u min, greater than u max. That's fine. That's okay. That's an input. Those are input limits. Sorry, and before we go on, hopefully we have time this semester. I've always wanted to cover this in one of these classes. You might be saying, is there no way to try to avoid going to a bad state? We can penalize them in the cost. You don't want to leave the workspace. You don't want to hit my student. You don't want to bump into them, right? But a penalty is just a suggestion, right? A cost is a suggestion. It's like, I want to be able to go somewhere as well, do this as best as I can. If I can't do it, it's fine, right? Well, very clever people have found ways to set up costs and constraints in certain circumstances to guarantee you won't do anything you don't want to do. It's very tricky. There are very specific conditions you have to meet, okay? But they're called barrier functions or safety functions, where that exact scenario we were talking about, that I'm going so fast, that I'm going so fast that I leave the workspace, right? It will try to automatically slow you down so that way you never go so fast as you leave the workspace, right? The math to proving how it works is a bit tricky. It's something that requires a little bit more prerequisites than we have in this class, but I can show you the math to actually to implement it, and it's not as bad as you might think. If you can take it in this class, if you can take a derivative, you can do the math you need. All right? See here? Sorry, I forgot to pull it up. So we can penalize constraints in the cost. We can put input limits here. All right? Okay, so now we want to penalize in the cost. Okay, our cost function. What I would like to do is have something like the integral from 0 to time, to the end of our time horizon, of our s desired minus s of t squared plus s dot of t squared dt. What did I just do? I just threw math at you, okay? This right here, this is our error, right? This is where we want to go. This is where we are. That's our error. If we square that error will always be positive. That's good. So minimizing it, we'll try to take it to 0. That's good. And here, it's penalizing when we are moving fast. Right? Faster we move, positive or negative, the worse, right? So it would try to bring us to a stop, right? Then I'm integrating it, so I'm saying over the entire trajectory, the longer that we stay away from our final position, the worse it is. So it's like, get there fast, please. Okay? Now this integral is a continuous integral, but keep in mind we have these discrete SKs and UKs involved. So what that would look like, our cost function, J of W, going to be equal to the sum from I is equal from 1 to n minus 1 of S desired minus SK plus squared plus S dot K squared all times delta T, which you all, of course, know is T over n minus 1. Okay. And you'll note that this cost, this is a quadratic cost. And you can check by taking that cost and taking the Hessian, the second derivative, and it should be full of constants. Okay? Hessian is constant. Okay? And I'm going to say one thing, and the only constraint on state that is allowable and needed is the initial condition. Okay? So that means that SK is equal to whatever your current time is, S right now, and S dot K is whatever your current speed is. And your decision variables are U1 through UK through UN, S1 through SK through SN, and call it S dot 1 through S dot K through S dot N, all as a column. There we go. That is our decision vector. Okay. Up above is our cost function. Right there. And up above is our defect constraints that enforce physics. And we have our input limits, these constraints. And we've got our initial conditions. All of our constraints are linear. Our cost is quadratic. And if we check the Hessian, it would also be positive. Positive eigenvalues. It's going to be convex. It's quadratic. It's fantastic. We have a quadratic program. This is a convex quadratic program. Or QP. Is a convex quadratic program a good thing to have for your optimization? Yes. Why? Why? Anyone remember? It's fast and reliable. Quite the thing to have. It's very important to have a fast and reliable optimization. When your control loop depends on it. Okay. We have definitely had in the laboratory that we've messed up setting up the optimization You screwed something up. And it was taking, and the optimization was sort of hanging. It was taking too long. And the robot was like stuttering, not knowing what to do, looked confused. Okay? Yeah. That's because we didn't set up the optimization right. Yeah. There are all kinds of tricks that you can do. What we talk about, like QPs in general are fast and reliable if they're convex, and that is true. There are limits. You know, if you're giving it thousands of variables, it'll still take more time than if you have 10 variables, right? So there are tricks to run fast. To running QPs faster. One is you can limit the number of optimization iterations. Okay? It might find something that's good enough, even if it's not optimal. Good enough, we need it now. We need an answer now. Okay? And number two, we haven't had to deal with this with QPs just because they've been so fast and reliable. But technically speaking, they needed an initial guess. When we were doing our nonlinear optimizations, we absolutely needed an initial guess, right? We said, hey, we're going to guess the answers are all 1s or 10s or things like that, right? And those are stupid guesses. We're getting away with stupid guesses. It's okay. They're working all right, right? But you can always give us smarter guesses, okay? You can, we call that is warm start. With an initial guess that is the solution to the last optimization. You're running lots of these optimizations all in sequence, right? We'll take the last solution you got, make that the initial guess for the next one. Probably going to be close by, right? So it may take fewer iterations to find the solution. Right? Okay. Those are two good tricks for making your QPs run faster. Because again, they are in the loop. All right. That takes us to the end of class here. MPC is pretty awesome. I love it. Look forward to coding that with you sometime in the next few weeks. Have a good one. See you on Thursday.